Before looking in detail at how to transform between different reference frames that are used for robot localization, let's first see how can we express in mathematical form the pose of a mobile robot in space, and most importantly, what is the pose of a mobile robot. We can simplify our mobile robot just as an object that is restricted to moving in a two-dimensional plane. So, assuming that we have a top-down view of the robot, it will only be able to move on the XY plane. Let's define a fixed reference frame called world, so indicated with W, and the problem of defining the pose of the robot in the two-dimensional space simply becomes the problem of defining the position and the orientation of an object with respect to a fixed reference frame, that is, the frame W of the world. To further simplify this concept, let's introduce another reference frame. This time, this is a mobile reference frame that is attached to the robot and so that moves along with the robot. This second reference frame is called R. This is a mobile reference frame since it moves along with the robot, and for this reason it is called inertial frame. As we can see, now, while the reference frame of the world is fixed and remains fixed, and therefore is a non-inertial frame, the reference frame R, so the one that is attached to the robot, moves along with it, and that's why it is called inertial. Thus, the problem of defining the pose of a robot in a two-dimensional space now becomes the problem of defining the position and the orientation of the reference frame R with respect to the frame W. Having significantly simplified our problem, now we can intuitively say that we just need three variables to define the pose of the frame R with respect to the frame W. So the pose is defined by two variables that represents the coordinate x and y of the center of the frame R with respect to the center of the frame W, and the angle theta that represents the orientation of the frame R with respect to the frame W. Together, these three variables express the pose of one reference frame with respect to another, and therefore, since we consider that the frame R is attached to the robot and that moves along with the robot, these three variables also represent the pose of the robot as it moves in the two-dimensional space. Although we have already highly simplified our problem and we reduced it just to the calculation of three variables, we can simplify it even further and break it down into two separate problems. The problem, in fact, can be considered as the combination of two elementary components of the motions, that are the translation and the rotation. So we will study separately the position of the robot, which is defined by the x and y component of the pose, and the orientation, so the rotation of the robot, that instead is defined with the angle theta. Then, after studying each component separately, we will combine the results into the more general roto-translation motion.